Now, I said that we can't factorize some of those quadratics. That was a little white lie. We can, of course, factorize all quadratics. The answer might look a little unusual, but we can do it. And completing the square can help us do that. So here's one that actually we could solve. What is it? I mean, we could factorize. Let's pretend that we go, oh no, multiplies together give negative 7, adds together give 6. That's not possible. What numbers on earth could do that? Can't work that out. So completing the square, the idea of completing the square, move the constant. So we get the 7 over the other side. We add half the coefficient, and this is where your grammar's important, of x squared. Not half the coefficient of x squared, but half the coefficient of x squared. Okay? So half the coefficient of x is 3, and we square it. And what that does, of course, is on the left-hand side creates a perfect square. There it is, x squared plus 6x plus 9, which of course becomes x plus 3 all squared. And so we're now saying something all squared is 16, so therefore that must be either plus or minus 4. And so we get negative 3 plus or minus 4, so minus 7 and 1. So they're basically the steps for a traditional way of completing the square. This is, in fact, where the quadratic formula comes from. And because what we do in maths is, it's patterns. Because if you're going to go and solve that, I just spelled out the steps. You do the same steps every time. If you're going to do the same steps every time, then that will lend itself to a formula. It's all right, let's do it with this. Well, the first thing I'm going to do is make it monic. Ax squared's a bit messy. We like it just to be x squared when we complete the square. So let's divide everything by a. I will move the constant to the right-hand side. So that's now minus c on a. I'll add half the coefficient of x squared. Well, the coefficient of x is b on a, so half of that is b on 2a. But we'll add it squared. Tidy that up. The left-hand side is now a perfect square. It's x plus b on 2a all squared. Ooh, a bit of algebraic fraction work on the right-hand side. Common denominator would be 4a squared. Oh, look at that. b squared minus 4ac all over 4a squared. Okay, I've got something squared equals that. So x plus b on 2a must be plus or minus the square root of b squared minus 4ac all over 2a. I then move the b over 2a. There's where our quadratic formula comes from. Okay? So it basically is a formula to save you completing the square every single time. Let's have a look at this. You see, I said that's the traditional way of completing a square. Here's another way of thinking about it. X minus 6x plus 6. I know that completing the square, I'm going to end up with x and then half the coefficient of x inside the perfect square. So I know I will end up with x minus 3 all squared. But if I was to expand that out, they're not the same. If I was to expand that out, I'd get 9. I don't want 9, I want 6. So to get from 9 to 6, I subtract 3. I now have the difference of 2 squares. Okay, the second one is the square root of 3 all squared. But what it means is it will factorize to be x minus 3 plus root 3, x minus 3 minus root 3. Two things multiplied together to give 0. So therefore, either x is 3 minus root 3 or 3 plus root 3. So that's an alternative way. It's still completing the square, but I think in a little bit of a neater sort of way. That sort of thinking comes in very useful in an extension 2 topic of complex numbers, where we start dealing with imaginary numbers and what have you. All right, that'll do us for today.